In this video I'm going to be talking about the critical numbers that we use in calculus. We're going to give a definition of them, show you how to find them algebraically, just kind of play with this idea of critical numbers. Alright, to start with, we have a definition. We're going to let f be defined at c. Alright, and this is an extremely important part that is often overlooked. You've got to make sure that the function is defined at c if we want c to be a critical point. If the derivative equals 0, or if f is not differentiable at c, then c is going to be a critical number of your function. Alright, so over here I've got a couple of examples of what we just said there. Alright, in this picture right here, I've got a cusp going on at x equals c. Alright, so therefore I can say that x equals c is a critical number because the derivative at c does not exist. Alright, another possible scenario here would be maybe, say, an upside down parabola, and c being right there at that maximum point. Alright, the derivative is 0 right there because you've got a horizontal tangent, so your derivative is equal to 0, so therefore x equals c is a critical point. Alright, so that's taking the definition and kind of putting it into a picture form to look at. Alright, now there's a theorem that corresponds to this as well, that just basically says if f has a relative max or min at x equals c, then c is a critical number of f. So if you know it's going to, if you can look at your function, somehow know that you've got a relative max or relative min, then you're guaranteed those are going to be critical points. Okay, now let's work out a couple examples here, maybe 3 examples of showing you how to algebraically find those critical points, okay, assuming that we do not have a picture of the graph or anything. Alright, so I've kind of summarized what we're going to do here. If we're trying to find our critical numbers, we're going to take our function and we're going to find the derivative. We're then going to set that derivative equal to 0. Alright, and hopefully it's going to factor pretty nicely and you're going to be able to solve. Regardless, you're going to set that derivative equal to 0 and attempt to solve. Alright, and then these answers are going to be your critical numbers. And there again, you need to make sure that the function is defined at those values to actually call them critical values. Alright, so taking a look at this first example here, I've got f of x equals x to the 4th minus 9x squared. Alright, that's a polynomial curve, so it's nice, smooth, continuous. Alright, it's going to be differentiable everywhere. It's going to be, all reals for your domain. So whatever values we find for c, we can be assured that they are defined for this function. Alright, so the first thing we're going to do is we're going to find the derivative. Alright, straightforward derivative here. We'll have a 4x to the 3rd minus an 18x. Alright, now we're going to take that derivative and we're going to set it equal to 0. So 4x to the 3rd minus 18x equals 0. Alright, I think I can factor out the greatest common factor here, which is going to be a 2x. So I'm going to take out a 2x. 4x to the 3rd, take out a 2x, will leave me with a 2x squared. And the 18x, take out 2x, that'll leave me with a minus 9. Okay, at this point you're going to use the zero product principle where you're going to set both of those things equal to 0 to continue to solve it. So if I set 2x equal to 0, then x equals 0. And if I set 2x squared minus 9 equal to 0 and solve, I'm going to have a 2x squared equals a 9. X squared equals 9 halves. Let's just go ahead and leave it as 9 halves. I can do x equals plus or minus the square root of 9 halves, which I can simplify that numerator at least there. So x is going to be plus or minus 3 over square root of 2. Alright, depending on how far you want to simplify this, if you need to rationalize that, you can. Alright, otherwise you could just leave it like that. Alright, so critical numbers for this first one, x equals 0 and x equals plus or minus 3 over square root of 2. Alright, so that's pretty much a straightforward example with a polynomial curve. Alright, if we take a look at a couple others, okay, let's do a quotient here on the left as my next example. Let's do f of x equals 2x over an x squared plus 1. Okay, so it is a rational function, alright, but I can set that denominator equal to 0. X squared equals negative 1, take square root of both sides. I can clearly see there's not going to be any vertical asymptotes here, so we're probably going to be pretty safe to assume that whatever we find here is going to be our critical numbers. So, because everything will be defined. So, let's see, first derivative here. Okay, so we've got to do quotient rule on that. So the bottom, x squared plus 1, times the derivative of the top, which is 2, minus the top, 2x, times the derivative of the bottom, so 2x. And then all over the bottom squared. So x squared plus 1 quantity squared. Alright, now let's do a little simplifying here. This right here is going to give me a 2x squared plus a 2, and this will just be a minus 4x squared. Denominator is not going to change. Okay, so let's go ahead and simplify a little bit farther. That's going to make my numerator a 2 minus 2x squared all over x squared plus 1. Alright, now we need to set that equal to 0 and solve. Basically what you can do is you can just set the numerator equal to 0, you can set the denominator equal to 0, and find your critical points that way. So let's kind of break it up into two little things here. I'm going to go 2 minus 2x squared equals 0. I'm going to solve this equation, so 2 equals a 2x squared. Divide both sides by 2. I'm going to have an x squared equals 1. So that'll be an x equals a plus or minus 1 right there when I take square root of both sides. Now let's take that denominator and do the same thing. Set it equal to 0. Alright, square root of both sides. X squared plus 1 still equals 0. X squared equals a negative 1. When I take square root of both sides on this one, I'd have plus or minus the square root of a negative 1. Alright, so that's going to be imaginary numbers. So here, they're not going to give me any critical numbers. So no critical numbers from here because they're imaginary. Okay, so no critical numbers here. So that means my only critical numbers for this equation are going to occur at x equals plus or minus 1. Alright, so another one, pretty straightforward example there, except it is a quotient. And you got to use quotient rule. When you get down, just remember set both the numerator and the denominator equal to 0 so that you can find all your possible critical numbers on that. Okay, now, inevitably, probably, you're going to have to do some trig functions, maybe even some exponential functions of those natures as well. But I thought I would pick a trig example here. So f of x equals 2 secant x plus tangent x. Okay, so the first thing I need to do is find my derivative. Alright, so derivative of secant is secant tangent. So 2 secant x tangent x. Alright, and the derivative of tangent is secant squared. So secant squared x. So a pretty simple derivative there. Alright, now looking at this, I think I'm going to factor out a secant x out of both of those terms when I set it equal to 0. So if I factor out a secant x, in that first term there, I'll be left with a 2 tangent x. And then I've got 2 secant x's here. Take one of them out. I'll only have one left there. Now we can set that equal to 0 and we can solve. Okay, so if I set this one equal to 0, secant x equals 0. Alright, that's going to be kind of hard to solve, so do some algebra here, do some substitutions. Secant is the same thing as 1 over cosine x. Alright, and then if I want to turn this into a fraction on this side so I cross multiply down, I could do something like 0 over 1. That gives me a nice little proportion there if I'm trying to solve. 0 times cosine x is just going to be 0. 1 times 1 is going to be 1. Well, 0 does not equal 1. That's a false statement. So there's no critical numbers here. So no critical numbers. Okay. Alright, and then taking this one and setting this equal to 0, this one will be a little more challenging to solve. You might want to grab a calculator. You could put this into y1, you could put this into y2, and then you could look to see where they intersect and solve it that way. Okay, but you can also do this by hand. Alright, if I do a substitution on tangent, I would have 2 times sine x over cosine x. Alright, plus, now let's do a substitution for secant as 1 over cosine x, still equal to 0. Alright, now I can add these fractions, because I now got common denominators, so really on top I'm going to have a 2 sine x plus 1 all over cosine x equals 0. Multiply both sides by cosine x, so basically the cosine x is going to go away. So I'm going to have a 2 sine x plus 1 equals 0. Subtract 1 from both sides. 2 sine x equals a negative 1. Divide both sides by 2. So sine x equals a negative 1/2. Alright, and then you could just at this point use your unit circle Alright, go around, look at your unit circle, find where sine equals -1/2, and then, well, what angle measure is that? If you're doing it in radians and you compare that on a unit circle, I think you're going to find that it is 7 pi over 6 and 11 pi over 6. Okay, so there were no critical numbers here, but from this equation being able to solve it by hand, I was able to find 7 pi over 6 and 11 pi over 6, given it in radian measures there. Okay, so 3 examples of how you go about finding critical numbers. Alright, gave you the definition at the beginning with the theorem that comes along. Alright, this is a very handy tool. This is going to lead into curve sketching and things of that nature. But you definitely want to be able to do it with any given type of equation, no matter what it is. So be able to find that derivative, set it equal to 0, and then be able to solve that derivative. Definitely thanks for watching, and don't forget to subscribe to the channel. Thanks.